On June 29, 2022, Earth completed one full rotation in less time than it ever had since scientists began measuring with atomic precision. The day was shorter than usual by 1.59 milliseconds. That sounds trivial. It sounds like a rounding error. But when a planet 4.5 billion years old starts rushing through its own rotation cycle faster than at any recorded point in modern history, scientists pay attention. And when it happens not once but repeatedly, year after year, the question stops being, is this real? And becomes something far more interesting. What is driving it? The answer reaches from the surface of the planet all the way to its core. And the story involves some of the strangest confirmed science on Earth right now. Let's start with what a day actually is. It is not 24 hours. Not exactly. A day is the time it takes Earth to complete one full rotation, and that duration has never been fixed. The planet has always fluctuated slightly, speeding up and slowing down by tiny amounts depending on forces acting on it from inside and out. The long-term trend, the one that has held for most of recorded history, was gradual slowing. The moon's gravitational pull drags at the oceans like a brake, shedding milliseconds from the day across millions of years. Ancient coral fossils confirm it. Corals from 400 million years ago show approximately 400 growth rings per year, meaning the year held more days because each day was shorter. The planet has been spinning down ever since. That slow deceleration is the baseline. It is the expected direction of travel, which is precisely why what happened around 2016 stopped researchers cold. The trend reversed. Earth started speeding up. Not dramatically. Not in a way you would notice in your morning routine, but measurably, consistently, year after year. 2020 set a new record for the shortest day since atomic timekeeping began. 2021 broke it. 2022 shattered it. The planet logged some of the briefest rotations in modern instrumental history, all while the forces responsible for slowing it, tidal friction, atmospheric drag, remained operating normally. Something else was pushing back, hard enough to overcome the moon's perpetual brake. That is the puzzle. And the candidates responsible for this push reach from the ice sheets at the poles all the way down to a sphere of solid iron spinning at the very center of the planet. To understand why a millisecond matters, picture every major system on Earth as a choir. Every server, satellite, database, and network node is a singer. They all follow the same sheet of music, coordinated universal time. Their job is to stay perfectly synchronized, millisecond by millisecond. Now remove one note from the score without telling every singer simultaneously. Some skip it cleanly. Others pause, waiting for a note that never comes. Others jump ahead. In an instant, voices that were synchronized begin to split apart. That is roughly what engineers fear when Earth's rotation drifts out of step with the atomic clocks we have built our civilization around. Here is the background you need to understand why this matters. Before 1955, the most accurate clocks on Earth lost or gained about 1 second every 300 years. That sounds impressive, until you realize planetary science requires something far more precise. Then physicists built the first atomic clock. The principle is elegant. Atoms do not lie. Every atom of the same element anywhere in the universe vibrates at exactly the same frequency. Cesium-133 atoms oscillate 9,192,631,770 times per second. Every single time, without exception, without drift. That frequency became the new definition of a second. Not a fraction of Earth's orbit, not a pendulum swing, the measured vibration of a single type of atom. The result was a clock so accurate it would not gain or lose 1 second across 300 million years. With that level of precision suddenly available, scientists could do something they had never done before. They could measure the planet with real fidelity. And what they found was unsettling from the start. Earth's rotation, it turned out, was messy, constantly fluctuating. The planet sped up slightly in northern hemisphere winters as atmospheric mass shifted toward the poles. It slowed in summer. Major earthquakes made tiny adjustments. El Niño events, changes in ocean circulation, even large snow accumulations at high latitudes left faint signatures in the rotation record. Scientists catalogued these variations and accounted for them. The system worked. A correction mechanism called the leap second, invented in 1972, periodically added 1 extra second to the official clock to keep atomic time aligned with Earth time. 27 leap seconds have been added since the system began. Not one has ever been removed. The planet was always slowing, which meant atomic clocks always ran ahead of Earth, which meant the fix was always to add time. Then came the data from 2016 onward. The fluctuations were still there, but underneath them a clear signal was emerging. The average length of a day was shrinking, not randomly, not as a seasonal variation that would correct itself, as a trend. And when scientists subtracted every known contributing factor from the data, atmospheric shifts, tidal friction, ocean currents, a residual acceleration remained. Something beyond the catalogued causes was pushing the planet forward. They had a measurement without a complete explanation. For the first time in the history of the leap second system, the discussion shifted from adding time to removing it. A negative leap second. And the engineers responsible for global internet infrastructure have described that scenario on record as one of the most dangerous things that could happen to digital systems worldwide. Here is the technical reality. A negative leap second would mean clocks tick from 23:59:58 directly to midnight. The second 23:59:59 would simply not exist. Every system expecting that second, every log file, every transaction, every scheduled process timed to that moment would encounter a gap, a hole in time. Engineers at Meta published a paper describing the potential consequences, calling the negative leap second an event with a devastating effect on software relying on timers or schedulers. Their recommendation was to never apply one. Google, Amazon, and Microsoft all developed their own workaround approaches. None arrived at the same solution, which means, in the event of a negative leap second, the largest technology companies on Earth would be running subtly different versions of time simultaneously. Financial markets are perhaps the clearest example of how this kind of desynchronization cascades. High-frequency trading systems execute thousands of transactions per second. Order books match buyers and sellers based on precise sequence. If one exchange's clock jumps backward while another's does not, the sequence of trades becomes ambiguous. Transactions that appeared settled become disputed. Trades placed after the subtracted second might be logged as occurring before trades placed ahead of it. Some regulatory jurisdictions require financial institutions to maintain records accurate to the microsecond. A 1-second reversal does not just create confusion, it creates legal liability. Power grids face a different version of the same problem. Alternating current flows at a fixed frequency, either 50 or 60 cycles per second, depending on the country. Grid operators synchronize their systems to universal time to balance electricity loads across regions. A sudden discontinuity in time creates a window where the coordination signal breaks down. Backup systems compensate quickly in most cases, but the industry has a term for what happens in the gap: a synchronization event. And synchronization events, even brief ones, are the precursor to the kind of cascading failures that can bring down large sections of a grid. Aviation adds another layer. Air traffic control systems depend on synchronized timestamps to track aircraft positions and resolve conflicts between flight paths. When controllers at different facilities work from clocks that disagree even briefly, the margin built into separation standards gets consumed by the ambiguity. Satellite navigation adds yet another. Global positioning system satellites orbit at a precisely calculated path and broadcast signals timed to nanosecond precision. When Earth rotates faster than expected, the surface moves ahead of where the satellites predict it to be. The resulting positional error might be a few centimeters to a few meters. For a family finding a restaurant, irrelevant. For a cargo ship navigating a narrow strait at night, or an aircraft making a zero visibility instrument approach, it is the difference between safety and catastrophe. In 2022, an international standards body voted to eliminate the leap second entirely by 2035, allowing atomic time and Earth time to drift without correction until a different mechanism could handle the gap. That decision sounds like a clean solution. It is not. It simply defers the problem, and the gap is compounding in a direction nobody planned for. Here is the harder question. Not why the timekeeping system is struggling, but why the planet accelerated in the first place. If you could drill straight down through the crust, through miles of rock, through the upper mantle, through the lower mantle, past the point where pressure becomes so extreme that atoms are forced into configurations that do not exist at the surface, you would eventually reach the outer core. It begins roughly 1,800 miles down. It extends another 1,400 miles further in. It is composed primarily of iron and nickel. It is hotter than the surface of the star we orbit, and it is entirely liquid. Not liquid like water, liquid like a metal so compressed and energized that it flows in massive currents, driven by the temperature difference between the cooler base of the mantle above and the intense heat of the solid inner core below. Those currents move at surprising speeds, tens of miles per year, and they carry electrical charge. Flowing liquid iron generates a magnetic field through a process called the geodynamo. The currents create electrical currents. The electrical currents create magnetism, and that magnetism extends outward from the core through the mantle, through the crust, and out into space, forming the protective bubble that deflects charged particles from the sun. Without it, those particles would strip the atmosphere away and scour the surface bare. The liquid outer core is, in a very direct sense, why Earth is livable. But it does more than generate the magnetic field. It physically interacts with the rotation of everything above it. The outer core does not rotate at exactly the same rate as the mantle and crust. There is a coupling between them, transmitted through pressure and electromagnetic forces, but the core has some rotational independence. When the currents inside it shift, when massive columns of rising and sinking iron change their flow patterns, they exert torque on the layer above them. That torque shows up in the rotation data. Researchers studying the correlation between changes in Earth's magnetic field and changes in rotation rate have found a consistent pattern. When the field fluctuates in certain ways, the rotation tends to change. The connection is still being worked out mechanistically, but the correlation is strong enough that geophysicists now treat core dynamics as a primary driver of decade-scale rotation variations. The surface acceleration that began around 2016 coincides with changes in the outer core's circulation pattern detected in satellite magnetic data. The timing is not a coincidence, and the outer core does not move in isolation. It wraps around something at the very center of the planet, something solid, something with its own rotation rate, its own angular momentum, and its own relationship with the layers above it. The inner core. At the center of Earth, roughly 3,600 miles beneath your feet, there is a sphere of solid iron roughly as wide as the moon. It exists in a state that should not be possible by ordinary standards. The pressure at that depth is more than 3 million times the atmospheric pressure at the surface. The temperature is roughly 9,000 degrees Fahrenheit, comparable to the outer layer of the sun. At that temperature, iron should be liquid. Nearly everything should be liquid. But it is not. It is solid. And it is solid precisely because of the pressure. The weight of the entire planet pressing inward forces the iron into a crystalline structure so tightly packed that the heat cannot shake it apart. The inner core floats inside the liquid outer core the way a ball bearing floats in oil. It is not connected to the mantle or crust by any rigid material. The liquid iron surrounding it provides the only medium through which forces can be transmitted between the innermost sphere and everything above it. That means the inner core can rotate independently. For decades, geophysicists suspected it did. The evidence came from an unusual source: earthquakes. When a major earthquake strikes, it sends seismic waves radiating outward in all directions, including straight down through the core and up the other side. Seismograph stations positioned strategically around the globe record those waves and use the travel times to map the interior. Different materials transmit seismic waves at different speeds. The inner core, with its iron crystal structure aligned in a particular orientation, transmits waves slightly faster along certain paths than others. By comparing seismic recordings of similar earthquakes over decades, scientists found that the travel times were changing. Waves passing through the inner core were arriving at slightly different times in recent decades than they had in earlier records. The best explanation: the inner core was rotating faster than the mantle above it, slowly turning relative to the surface, changing the orientation of its crystal structure relative to the paths the waves were traveling. Then, in 2023, a study published in the journal Nature Geoscience drew a different conclusion from a longer dataset. The inner core had been rotating faster than the surface through the 1990s. Sometime around 2009, it slowed to match the surface. Around 2010 to 2012, it appeared to slow further, rotating slightly slower than the mantle above it. The conclusion the researchers reached was this: the inner core had reversed its rotation relative to the surface. It was now turning fractionally in the opposite direction from the planets surrounding it. Sit with that for a moment. The solid iron center of Earth, turn after turn, is now spinning opposite to the rest of the planet you live on. The forces involved are enormous. The angular momentum of the inner core is not a small quantity. Its changes in rotation coupled to the outer core, which couples to the mantle, which couples to the crust. Each coupling is imperfect. Each introduces a delay, a torque, a transfer of rotational energy that propagates upward through the layers. Some researchers believe the inner core's reversal is directly linked to the surface acceleration. The mechanism works like this. When the inner core decelerates, that angular momentum does not disappear. It transfers through electromagnetic and gravitational coupling to the outer core. The outer core passes it to the mantle. The mantle passes it to the crust. Angular momentum moving upward through those layers is angular momentum being added to the rotation of the surface. It is the equivalent of a figure skater pulling their arms inward to spin faster, except the energy is traveling from the innermost layer outward, and the surface speeds up as a result. The timeline fits. The inner core's apparent deceleration in the late 2000s and early 2010s, when combined with the lag time expected for a signal to propagate upward through those layers, aligned with a surface acceleration that became clearly measurable starting around 2016. That lag is scientifically important in its own right. It suggests the coupling between the inner core and the surface is not instantaneous. Information from the center takes years to decades to travel upward through the system, which raises a question nobody has a clean answer to yet. If the reversal is real and continuing, what does the surface look like at the far end of this angular momentum transfer? It is worth being precise about the science here. This is not settled consensus. The 2023 Nature Geoscience study by Yang and Song has credible critics. Those critics argue that alternative explanations exist. Topographic features on the inner core surface, irregular ridges and valleys of iron crystal, could scatter seismic waves differently over time without requiring any rotation at all. Changes in the structure of the outer core above could also affect wave travel times without the inner core moving. What both sides agree on is simpler and more important than the reversal debate itself. Something changed inside the planet. The inner core's behavior in the 21st century is different from its behavior in the 20th. And that difference, whatever its precise nature, connects upward to the surface through mechanisms that the field is still working to fully characterize. While the core drives things from the inside, the surface of the planet is being simultaneously reshaped by something at the poles. In physics classrooms, there is a demonstration that never fails to impress. A person sits on a rotating stool holding two weights, one in each hand, arms extended. The stool spins slowly. Then they pull their arms inward, bringing the weights close to their body. The stool speeds up dramatically without anyone pushing it. No energy was added. No external force was applied. The person simply moved mass closer to the rotation axis. In doing so, they conserved angular momentum, and the rotation rate had to increase to compensate. Earth works by the same principle. For most of the last 20,000 years, massive ice sheets covered large portions of the planet's surface, concentrated primarily near the poles. Ice near the poles sits close to Earth's rotation axis. When that ice melts and flows into the oceans, it redistributes away from the poles and spreads across lower latitudes, moving mass away from the rotation axis. Physics says this should slow the rotation, and for most of the Holocene, that slow post-glacial rebound effect has been doing exactly that. But something has changed in the rate. The Greenland ice sheet and the West Antarctic ice sheet are now losing mass at rates that have accelerated sharply since the 1990s. Greenland alone is losing roughly 280 billion metric tons of ice per year. Antarctica is losing roughly 150 billion metric tons per year. Those numbers are large enough to detect from space. The Gravity Recovery and Climate Experiment satellites, known as GRACE and its successor GRACE Follow-On, measure tiny variations in Earth's gravitational field by tracking the distance between two satellites flying in formation. When mass shifts on the surface, the gravitational field shifts with it, and the satellites drift closer together or further apart by a fraction of a micrometer. Using that data, scientists have directly mapped the redistribution of mass as ice melts. The picture is striking. The poles are losing mass. The mid-latitude ocean basins are gaining it. Earth's moment of inertia, the rotational equivalent of mass distribution, is shifting in real time, and that shifting is moving in a direction that should produce a long-term deceleration. But here is the short-term complication. The redistribution is not uniform. Different parts of the ice sheet melt at different rates. Different ocean basins accumulate water at different depths and latitudes. The interaction between where mass is going and how that interacts with Earth's three-dimensional shape produces effects that are not simply the sum of their parts. One of those effects is that the planet's rotation axis is physically moving, not the magnetic North Pole, which is a separate thing. The actual spin axis, the imaginary line through the planet around which everything rotates. It has shifted by measurable amounts in the last 2 decades in a direction that directly aligns with the observed ice loss pattern. This is confirmed by satellite data. It is not a model prediction, it is a measurement. For most of the 20th century, the geographic North Pole drifted slowly toward northern Canada at a rate of a few centimeters per year. The cause was primarily post-glacial rebound, the continuing adjustment of the crust and mantle to the removal of the massive ice sheets that covered North America and northern Europe during the last ice age. Then, around the year 2000, the direction of drift changed. It turned eastward toward Greenland. The rate increased substantially, from a few centimeters per year to roughly 17 centimeters per year over the course of the 2000s and 2010s. When researchers analyzed the cause of this directional shift, the answer came back clearly from the GRACE satellite data. The primary driver was accelerating ice loss from Greenland. Greenland sits in a specific location relative to the polar drift trajectory. As its ice sheet loses mass, it changes the distribution of planetary mass in a way that pulls the pole in a new direction. The correspondence between the onset of accelerated Greenland ice loss and the shift in polar drift direction is close enough that scientists treat them as directly linked. Western Antarctic ice loss has also contributed. Every system that uses the precise location of Earth's rotation axis in its calculations has to be continuously updated to account for the drift. The International Earth Rotation and Reference System Service publishes updated Earth orientation parameters regularly, and those parameters feed directly into the correction models used by satellite navigation systems globally. The updates have been coming faster in recent years, and the rate of ice loss is not slowing, it is accelerating. The mass redistribution from ice loss does not just shift the axis, it changes how the planet responds to other forces acting on it. One of those responses is a slow rhythmic rocking called the Chandler wobble, and it has one of the stranger recent histories in Earth science. Earth does not spin on a perfectly stable axis, it wobbles. Multiple overlapping wobbles, each with its own period and cause, combine into a complex drift of the geographic poles that scientists have been tracking with increasing precision since the late 19th century. The Chandler wobble, named after American astronomer Seth Carlo Chandler, who documented it in the 1890s, is a slow cyclical rocking of the rotation axis relative to the solid body of the planet, repeating roughly every 14 months. The cause is geometry. Earth is not a perfect sphere, it is slightly flattened at the poles and bulging at the equator. A non-spherical rotating object does not spin in perfect alignment with its geometric axis. It wobbles around it, the way a football tumbles slightly as it spirals through the air. The Chandler wobble traces a small circle, roughly 30 feet across at the pole, that repeats on its 14-month cycle. Superimposed on it is an annual wobble caused by seasonal shifts in atmospheric mass and ocean loading. The combination produces a beat frequency that traces a slightly irregular ellipse over periods of about 6 years. It has been one of the most predictable features of Earth's rotational behavior for as long as it has been measured. Then, around the year 2000, it started behaving differently. The amplitude of the wobble, how large the circle traced by the pole was, began to decrease. By around 2005 to 2006, the Chandler wobble had dropped to roughly 1/5 of its typical amplitude. It had nearly vanished. Papers were published. The scientific community debated what could cause such a suppression. The leading hypothesis pointed to a redistribution of ocean bottom pressure. Deep ocean currents, specifically changes in where cold, dense water sinks to the ocean floor, had shifted in a way that damped the excitation that keeps the wobble going. Ocean temperature changes associated with a prolonged La Niña cycle were identified as a likely contributor. The wobble eventually recovered. By the late 2010s, it was operating closer to its normal amplitude again. But the episode revealed something uncomfortable. A force as fundamental as the Chandler wobble, operating for as long as Earth has had its current shape, had been significantly suppressed by changes in ocean circulation. If ocean changes could do that, other changes could suppress or amplify other fundamental rotational features. And if the ice redistribution continues at its current rate, and if the core dynamics continue to evolve, the combination of effects on Earth's rotation could take the system outside any behavior observed in the modern instrumental record. At that point, the only reference left would be the deep past. There is a library inside the planet, not books, not symbols, physical records left in stone by the magnetic field of past eras, pressed into cooling rock at the moment it solidified, never altered afterward. When lava erupts and cools into basalt, tiny magnetic minerals in the rock align themselves to the direction and intensity of Earth's magnetic field at that exact moment. They freeze in place as the rock hardens. The record they carry can survive for hundreds of millions of years without degradation. Using this method, paleomagnetists have mapped the history of Earth's magnetic field going back more than 4 billion years. They are not reading a smooth, stable story. They are reading a history of reversals. The polarity of Earth's magnetic field has flipped roughly every 200,000 to 300,000 years on average, though the timing is highly irregular. The last full reversal, called the Brunhes-Matuyama reversal, occurred roughly 780,000 years ago. By average statistics alone, we are overdue. That statement requires immediate context. The word overdue does not carry the same meaning here as it does for a dental appointment. The gap between reversals ranges from tens of thousands to tens of millions of years. Being past the average interval tells us almost nothing about when the next one will occur. What it does tell us is that reversal is a normal part of Earth's behavior. It has happened hundreds of times. Life has survived every one of them. But survived is doing some work in that sentence. During a reversal, the field does not simply flip instantaneously. The transition takes thousands of years. During that transition, the field weakens significantly, potentially dropping to 10 to 20% of its normal strength globally. The protection against charged particles from the sun is reduced across most of the planet. Increased radiation reaching the surface would elevate cancer rates. It would intensify damage to satellites and power grid infrastructure. It would affect animal navigation systems that depend on magnetic sensing, including migratory birds, sea turtles, and certain fish species. The atmospheric chemistry could be altered by the increased particle flux. Now here is the connection to rotation that closes the loop. The geodynamo that generates the magnetic field is powered by the same convective flows in the outer core that interact with the rotation of the planet. The field and the rotation are not independent systems. They are coupled. When the outer core's flow patterns change in ways that weaken the field, those same changes alter the electromagnetic torque on the mantle above. That torque affects the rotation rate of the surface. Researchers studying paleomagnetic records have found correlations between periods of field weakness and anomalies in paleoclimatic and geological records. The relationships are not fully understood, but they are real enough to warrant serious investigation. What makes the present moment particularly significant is the current rate of weakening. Global magnetic field intensity has declined by roughly 9% since measurements began in the early 19th century. 9% in roughly 180 years is a significant rate of change, and there is one region where the weakening is already extreme. The South Atlantic anomaly is a large region centered roughly over the South Atlantic Ocean and extending across much of South America, where the magnetic field is significantly weaker than the global average. In the strongest part of the anomaly, the field is roughly 40% weaker than it would be at equivalent latitudes elsewhere on Earth. That weakness has a consequence at altitude. Earth's magnetic field deflects charged particles from the sun, as well as higher energy cosmic rays from beyond the solar system. In most places, this protection begins at a sufficient altitude that satellites in low Earth orbit are shielded. In the South Atlantic anomaly, the field is so weak at lower altitudes that charged particles penetrate further before being deflected. Satellites passing through this region encounter elevated radiation levels that can cause electronic malfunctions. The International Space Station takes extra precautions when its orbit carries it through the anomaly. Astronauts are warned. Sensitive instruments are powered down or protected. What is new is that the anomaly is growing. It is expanding in area and deepening in its minimum intensity. It is also showing signs of developing a second minimum, a split into two separate weak spots, for which researchers have found evidence in current field data. The cause is tied directly to what is happening in the outer core beneath that region. Under the South Atlantic, there is an unusual structure in the outer core called a low-velocity zone, where liquid iron moves differently from the surrounding material. Some researchers believe this zone represents a patch of reversed magnetic polarity, where the local field alignment is opposite to the global dominant direction. The interaction between this reversed patch and the overall field above it produces the surface weakness. The reversed patch is not static, it is growing. This connects back to the rotation story in a way that is not immediately obvious. Changes in outer core flow patterns affect the magnetic field. Changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle. Changes in that coupling affect the transfer of angular momentum between the core and the surface. The South Atlantic anomaly is not just a radiation hazard for satellites, it is a visible symptom of changes happening in the outer core, the same outer core whose dynamics appear to be linked to the surface acceleration. Whether the current field weakening represents the beginning of a full reversal, a partial excursion that will correct itself, or something else entirely, is not yet determinable. What can be said is that the field is behaving differently today than it was 200 years ago. The outer core driving it is behaving differently than it was 2 decades ago. And the surface is rotating faster than it has in 50 years of precise measurement. These are all real measurements taken by calibrated instruments, reviewed and replicated across different scientific communities. The historical record preserved in basalt and coral and seafloor sediment gives us the only available baseline for conditions like these. Tidal rhythmites, layers of sediment deposited by tides, preserve a count of tidal cycles per year, which is directly related to rotation rate. Ancient coral is among the most famous of these recorders. Coral grows in daily and annual increments. The growth rings can be counted like tree rings. Corals from 400 million years ago, analyzed in the 1960s, showed approximately 400 growth rings per year, confirming a faster spinning planet. The paleomagnetic record tells us about field reversals. The sediment record tells us about rotation rates. The ice record tells us about mass redistribution. Taken together, they form a picture of a planet that has always been in motion, always changing, but doing so on timescales that dwarf the entire span of human civilization. Until now, the changes we are measuring were comfortably slow. Now, several of them are accelerating simultaneously. When researchers take the independently measured datasets from each of the systems described here and normalize them to a common scale on the same timeline, the result is striking. Outer core angular momentum estimates derived from magnetic field change rates show a departure from the 20th century baseline beginning around 2009 to 2010. Surface rotation data shows the acceleration beginning to emerge clearly from background noise around 2016, with the most extreme values appearing in 2020 through 2022. Greenland ice mass loss rate shows a step change increase beginning around 2012 and continuing to steepen. The South Atlantic anomaly's minimum field intensity shows a consistent decline with a steeper gradient emerging in the mid-2010s. Arctic sea ice extent shows its sharpest multi-year decline beginning around 2012. Atlantic meridional overturning circulation strength estimates show accelerating weakening in the mid-2010s. Each of these time series, measured independently by different instruments, different institutions, and different scientific communities, shows its major departure from the historical baseline in roughly the same decade-long window centered on approximately 2010 to 2020. The probability that 7 independent geophysical systems all departed from their historical baselines within the same decade by coincidence with no shared physical driver is not zero, but it is very small. What it suggests is that these systems share a common excitation. Something changed in the coupled Earth system during that window in a way that propagated across multiple layers simultaneously. Whether that something was primarily driven by the inner core, primarily by the ice and atmosphere system, or primarily by the magnetic transition, the effect was system-wide. And system-wide changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record shows that when multiple systems enter a departure phase together, they tend to remain in that departure for decades to centuries before finding a new equilibrium. And the equilibrium they reach at the end is not identical to the one they left. That last point is worth staying with. The equilibrium they find at the end is not identical to the one they left. The planet is not broken, it is not dying. Life has survived far more extreme geophysical transitions than this one across hundreds of millions of years. But the infrastructure of human civilization was not built to operate across a geophysical transition. It was built to operate in a stable period by the standards of geological time of extraordinary calm. The 10,000 years since the end of the last glaciation were unusually quiet. Rotation varied within a narrow band, the magnetic field was relatively stable, the ice sheets retreated at a manageable pace, sea levels rose gradually and then stabilized. In that stability, we built cities at coastal elevations that assumed sea level would not change rapidly. We built satellite infrastructure that assumed Earth would rotate predictably. We built power grids, financial systems, hospital networks, and navigation systems on the assumption that the clock would run smoothly and the poles would not move. Every one of those assumptions is now being tested, not catastrophically, not all at once, but consistently, and in a direction that creates increasing pressure on systems built for a different planet. The question the scientific community is working hardest to answer right now is not whether these changes are happening, they are. It is not whether they are connected, they appear to be. The question is how fast the transition will proceed, and whether the coupled feedbacks will stabilize at a new equilibrium within the next few decades or continue accelerating. If the system stabilizes within a generation, the engineering problems are manageable. The corrections needed are large but finite. Institutions that maintain global infrastructure have enough time to adapt. If the feedbacks continue to amplify, the window for managed adaptation narrows. The corrections needed grow faster than institutions can implement them. The systems with the least redundancy fail first, and their failures stress the systems connected to them. Neither outcome is certain. And the most honest answer from researchers closest to the data is that the uncertainty is larger than it was a decade ago, not smaller. More monitoring has produced more evidence of change. Better models have produced better resolution of the mechanisms. And better resolution has revealed how tightly coupled the systems are, which means how much a change in one can drive changes in others. Upcoming research efforts are trying to close the most critical gaps. New seismograph networks are being deployed to improve the resolution of the inner core data, to determine more precisely whether the rotation reversal is real and continuing, or whether alternative explanations for the seismic observations are more likely. Satellite magnetic missions beyond the current swarm constellation are being planned to track outer core circulation changes with higher temporal resolution. Ice mass monitoring from orbit is being extended and refined, with next-generation gravity satellite missions expected to improve the precision with which mass redistribution can be mapped in real time. Ocean circulation monitoring networks are being expanded in the South Atlantic region, specifically because of its role in the geomagnetic anomaly story. The geological record is also being read more carefully. Deep drilling projects through ancient lava flows are producing paleomagnetic histories at finer time resolution than previously available, trying to understand how past periods of field weakening related to rotation behavior, climate signals, and biological stress in the fossil record. What those projects are finding, consistently, is that the interactions between systems were always more tightly coupled than earlier models assumed. The planet is not a collection of independent geophysical processes. It is a coupled system where changes in one layer propagate through others in ways that take years to decades to fully express. That propagation delay is one reason the present situation is difficult to interpret in real time. The changes visible at the surface today may be the delayed expression of dynamics that changed deep in the planet years or even decades ago. And the changes happening in the deep planet today may not show up at the surface for years or decades to come. That is both a scientific puzzle and a practical challenge for the institutions tasked with maintaining the infrastructure that connects every person on Earth. The planet you live on is not static. It never was. It breathes, moves, shifts, and changes across timescales that dwarf recorded history. What is happening now is not outside the range of what Earth does, but it is outside the range of what Earth has done during the time humans have been building civilization on it. And the one question that science still cannot answer with confidence, the one that sits at the center of every model, every dataset, every late-night discussion in geodesy departments and geophysics laboratories, is deceptively simple. How fast? How fast are we moving toward the new equilibrium? That answer is being written right now in the rotation of a planet you are standing on, in the movement of ice you cannot see, in the churning of iron 2,000 miles below your feet. The instruments are running. The data is coming in, and some of the most important science of the next century will consist of reading it accurately enough to know what comes next. To fully appreciate the strangeness of what is happening right now, it helps to understand what normal looks like. And normal, in this context, stretches back not years or decades, but hundreds of millions of years. Earth formed roughly 4.5 billion years ago from the collision and accumulation of debris circling the young sun. It was initially a molten ball, spinning fast from the angular momentum of its formation. Days back then were somewhere between 5 and 6 hours long. The planet was rotating at nearly 4 times its current speed. Over billions of years, the gravitational tug of the Moon, which was then much closer than it is today, gradually transferred angular momentum away from Earth and into the Moon's orbit. The Moon slowly spiraled outward. Earth slowly spun down. That process continues today, adding approximately 1.4 milliseconds to the length of a day every century. It is the baseline trend, the geological expectation. Against that background, the acceleration measured since 2016 is not merely unexpected, it is a reversal of a trend that has been operating continuously for longer than complex life has existed on this planet. To truly understand the scale of what we are talking about, consider how scientists actually measure the length of a day. It is not simply reading a clock. It involves an entire global infrastructure of observatories using a technique called Very Long Baseline Interferometry, or VLBI. In this technique, radio telescopes on different continents simultaneously observe the same distant quasar, a galaxy so far away that its light takes billions of years to reach us and thus arrives essentially as a point source. By comparing the exact moment each telescope receives the signal from the quasar, accounting for their known separation, scientists can determine Earth's orientation in space to extraordinary precision. The method achieves angular measurements accurate to a fraction of a milliarc second, which corresponds to a physical displacement at Earth's surface of roughly 1 centimeter. This level of measurement is what caught the acceleration. Not a rough approximation, not a model prediction, an actual count of how quickly the planet is turning, cross-referenced with the cosmos itself. And the planet is turning faster. The acceleration is not large by any everyday standard. The total deviation between what the models expected and what the instruments measured amounts to a few milliseconds per day. But the instruments are sensitive enough that even those tiny deviations reveal something important. The signal does not look like random noise. It does not look like a seasonal variation that will reverse next quarter. It looks like a trend. Underneath the seasonal fluctuations, underneath the episodic variations from individual storms and earthquakes, there is a slow, steady component moving the average day length in one direction. That underlying signal is what geophysicists are trying to explain. And explaining it requires understanding how the different layers of Earth talk to each other. Think of Earth as a set of nested, rotating spheres. At the very center, the solid inner core. Surrounding it, the liquid outer core. Above that, the mantle, which is technically solid but flows on geological timescales like an extremely viscous fluid. Above the mantle, the crust, the thin, rigid shell we live on. And above the crust, the atmosphere, the oceans, and the ice sheets. Each of these layers has its own rotational inertia. Each couples to the adjacent layers through different mechanisms. The core couples to the mantle through electromagnetic forces generated by the geodynamo. The mantle couples to the crust through direct mechanical contact. The crust couples to the ocean and atmosphere through pressure and friction. Angular momentum can be exchanged between any of these layers, and when it is exchanged, the rotation rate of each layer changes. This is why the problem is so difficult. There is no single control knob labeled Earth's rotation speed. There is a web of interactions, feedbacks, and time delays that operate simultaneously across layers of different physical character at depths ranging from the surface to the center of the planet. What the current data shows is that something happened in the early 2010s that disturbed this web, and the disturbance propagated upward, eventually appearing in the surface rotation data starting around 2016. The lag between when something changed in the deep planet and when it shows up at the surface is itself a window into how tight or loose the coupling between layers actually is. The geodynamo, the process by which the liquid outer core generates Earth's magnetic field, is one of the most complex phenomena in planetary science. It is a self-sustaining electromagnetic system driven by heat, by the slow crystallization of iron at the inner core boundary, adding latent heat to the outer core, by radioactive decay within the core, and by the original heat left over from Earth's formation and differentiation. The outer core convects, meaning hot material rises while cool material sinks, creating large-scale fluid flows. These flows, in the presence of Earth's rotation, are shaped by the Coriolis effect into organized columns aligned with the rotation axis. These are called Taylor columns, and they are the primary structure through which the geodynamo organizes its electrical currents and produces its magnetic field. The Coriolis effect, the same force that makes hurricanes spin and deflects ocean currents, is fundamental to how the geodynamo works. When the rotation rate changes, the Coriolis effect changes. When the Coriolis effect changes, the organization of the Taylor columns changes. When the column organization changes, the magnetic field generated by them changes, and changes in the magnetic field feed back into the electromagnetic coupling between the outer core and the mantle, which in turn affects the rotation rate. This is a feedback loop operating across thousands of kilometers and decades of time. Understanding which direction it is currently moving and how fast is one of the central challenges in Earth science right now. The Swarm satellite constellation, a trio of satellites operated by the European Space Agency, is one of the primary tools for measuring these changes. Launched in 2013, Swarm carries magnetometers precise enough to detect changes in Earth's magnetic field at a level of detail that can be used to infer what is happening in the outer core below. The satellites essentially make the invisible interior of the planet visible by reading the magnetic field it generates. What Swarm has shown over its operational life is a planet whose deep interior is in active motion. The patterns of magnetic field variation associated with outer core convection have been shifting. Certain features, coherent fluid upwellings and downwellings in the outer core, have moved in position. The speed of field variations associated with core processes has changed, and the South Atlantic anomaly, the region of anomalous field weakness over the South Atlantic Ocean and South America, has continued to evolve in ways that suggest the low velocity zone in the outer core beneath it is growing. The low velocity zone is one of the most intriguing features in deep Earth science. It sits at the boundary between the outer core and the mantle, in a region called the core-mantle boundary, at a depth of approximately 1,800 miles. The material at this boundary is under extreme pressure and temperature, and it shows highly anomalous properties. In some locations, seismic waves slow dramatically as they pass through it, hence the term low-velocity zone. Some researchers believe these zones represent regions where liquid iron from the outer core has partially mixed with mantle material, creating a new phase of matter unlike anything accessible to direct study. The low-velocity zone beneath the South Atlantic has unusual magnetic properties. It appears to contain material with reversed magnetic polarity, meaning the local magnetic field points in the opposite direction from the global dominant polarity. This reverse patch sits close to the core mantle boundary and generates a local magnetic field that partially cancels the global field above it, producing the surface weakness we observe as the South Atlantic anomaly. The reverse patch appears to be growing larger. As it grows, the cancellation effect covers a wider area and deepens in intensity. If this process continues for long enough, it could contribute to triggering a full field reversal by destabilizing the global dipole structure. But this is where the science becomes genuinely uncertain. Whether the current patch represents a transient feature that will be swept away by the dominant global flow, or a nascent reversal structure that will continue to grow, is not yet determinable from the available data. What is clear is that the magnetic field over the South Atlantic is approximately 40% weaker than it should be for that latitude. What is clear is that the anomaly is expanding. What is clear is that satellites passing through it experience elevated radiation and electronic errors at a higher rate than those passing over other regions. And what is increasingly clear is that the dynamics of the outer core responsible for this anomaly are the same dynamics that couple to the surface rotation. The South Atlantic anomaly is not just a curiosity for satellite engineers. It is a window into the coupled behavior of the planet's deep interior systems. Earth's magnetic field reversal history is preserved with remarkable fidelity in the basaltic rock of the ocean floor. When magma erupts at mid-ocean ridges, the spreading centers where tectonic plates are born, it cools into basalt and records the magnetic field polarity of that moment. As the plates spread outward from the ridge over millions of years, they carry that magnetic record with them like a tape recording being played. The pattern of normal and reversed polarity stripes on either side of mid-ocean ridges, first recognized in the 1960s, confirmed plate tectonics and simultaneously provided a detailed timeline of past magnetic reversals stretching back hundreds of millions of years. That timeline shows several things clearly. Reversals are irregular. The current period of normal polarity, called the Brunhes Chron, is unusually long and approximately 780,000 years. Some crons have lasted tens of millions of years. Others were so brief, just a few thousand years, that they barely appear in the seafloor record. There have also been excursions, events where the field partially destabilized, weakened significantly, and then recovered without completing a full reversal. The Lachamp excursion, roughly 42,000 years ago, was one such event. the field dropped to about 25% of its current strength before recovering. There is evidence from ice cores and carbon-14 records that this excursion left detectable signatures in atmospheric chemistry and cosmic ray flux. Whether the current weakening represents the beginning of another excursion or something more persistent is, again, not yet determinable. But the rate of weakening is fast enough that researchers are paying attention in ways they were not 50 years ago. The connection between magnetic field strength and biological impacts is real, but often overstated in popular accounts. During past reversals and excursions, life on Earth continued. There is no clear mass extinction signal in the fossil record associated with the Brunhes-Matuyama reversal or the Lachamp excursion. However, the impacts were not zero. Studies of cave sediments and coral records from the Lachamp period show changes in cosmogenic nuclide production, isotopes created by cosmic rays interacting with the atmosphere, consistent with elevated radiation flux. There is evidence for disruption of the jet stream pattern. Some researchers have proposed connections between the Lachamp excursion and the timing of Neanderthal population decline, though this remains actively debated and the causal chain is not established. What is established is that the practical consequences of a significant field weakening for modern technological infrastructure would be substantially larger than anything earlier human populations faced. We have deployed a global network of satellites that are sensitive to radiation damage. We have built power grids that span continents and are vulnerable to geomagnetically induced currents when field activity is high. We have constructed navigation and communication systems whose accuracy depends on the predictability of the ionosphere, which is directly affected by the field's ability to deflect solar wind particles. A weakening field does not destroy these systems, but it stresses them in ways that require engineering responses. The good news is that even a reversal transition, were one to begin, would unfold over thousands of years. The timescale for technological adaptation is far shorter than the timescale of the geophysical change. The challenge is ensuring that the monitoring, planning, and infrastructure hardening happens before the stress becomes acute rather than in response to failure. On the ice side of the story, the changes are faster and already measurably affecting systems in the present. The GRACE and GRACE Follow-on satellites have fundamentally changed how we track mass changes on Earth's surface. Before these missions, most estimates of ice loss relied on surface measurements, aerial surveys, and physical models. These methods were accurate, but coarse. GRACE introduced a completely different approach, measuring the gravitational field itself. By tracking the precise distance between two satellites flying in formation, separated by roughly 220 kilometers, scientists measure how Earth's gravity pulls on each satellite differently as they pass over regions of varying mass. The measurement is extraordinarily sensitive. Changes in the distance between the satellites of less than 1 micrometer, a fraction of the width of a human hair, can reveal mass changes on Earth's surface equivalent to moving billions of tons of ice. The mass loss signal from Greenland and Antarctica is large enough to see clearly in this data. But the GRACE missions have revealed more than just total mass loss. They have mapped its geographic distribution, and the distribution is not uniform in ways that matter for rotation. Greenland's ice loss is concentrated in certain glaciers and coastal regions. The Jakobshavn Glacier on Greenland's west coast has been among the fastest retreating glaciers on Earth for the past 2 decades. The Helheim and Kangerlussuaq glaciers on the east coast have also shown dramatic acceleration. Each of these glaciers sits at a different distance from the rotation axis and in a different direction relative to the pole. Each therefore has a slightly different signature in the rotation and polar drift data. Separating these contributions from each other, and from the Antarctic contributions and the contributions of groundwater depletion, which is also detectable in GRACE data, is one of the ongoing challenges in interpreting Earth's rotational changes. Groundwater depletion adds an additional layer of complexity that is often underappreciated in public discussions of Earth's mass distribution changes. Human beings pump enormous quantities of water from underground aquifers for agriculture, industry, and drinking. That water, once extracted, eventually makes its way to the ocean through rivers, runoff, and evaporation and precipitation cycles. The net effect is a transfer of mass from underground reservoirs, which are distributed across all latitudes, to the ocean basins. Studies using GRACE data have found that groundwater depletion contributes measurably to sea level rise and to changes in Earth's moment of inertia. The contribution is smaller than that from ice sheets, but it is real and it is ongoing. The interaction between all these mass redistribution processes and Earth's rotation is mediated by something called the Love numbers, named after the British mathematician Augustus Edward Hough Love, who derived them in the early 20th century. Love numbers describe how a rotating elastic body responds to changes in its mass distribution. They capture the fact that Earth is not rigid but deforms slightly under the changing loads placed on it. When ice melts and mass redistributes, Earth's crust and mantle respond elastically, bulging where mass is added and rebounding where mass is removed. This elastic response itself affects the moment of inertia and therefore the rotation rate. Post-glacial rebound, the ongoing uplift of land in regions that were covered by ice sheets during the last ice age, is one manifestation of this. Scandinavia and Canada are still rising at rates of up to 1 centimeter per year as the mantle continues to flow in response to the removal of ice that has been gone for 10,000 years. The mantle flows, but extremely slowly. Its viscosity is roughly 10 to the 21st power times that of water. At that viscosity, it takes thousands of years to respond to the removal of an ice sheet. Earth is still responding to ice sheets that vanished at the end of the Pleistocene, and now it is beginning to respond to the accelerating loss of ice that is happening in the present. These two signals, the ancient rebound from 10,000 years ago and the fresh load change from modern ice loss, overlap in the rotation data in ways that are difficult to cleanly separate. Geodetic scientists use numerical models of mantle viscosity to try to subtract the ancient signal and isolate the modern one. But the mantle is not uniform. Its viscosity varies with depth, temperature, and composition. The models have uncertainties. Those uncertainties propagate into the rotation estimates. This is part of why the field is working hard to reduce the number of unknowns. Better seismic models of Earth's interior structure feed into better mantle viscosity models. Better mantle viscosity models produce better estimates of the glacial isostatic adjustment, the technical term for post-glacial rebound. Better glacial isostatic adjustment models produce better separation of the ancient and modern signals in the rotation data. And better rotation data produces better constraints on the core dynamics. The entire system of knowledge feeds back on itself, with improvements in one area propagating through the network. This is the current state of deep Earth science, not a discipline with clean answers, but one that is rapidly converging on better questions and sharper measurements. The oceanographic component of the rotation story is perhaps the least intuitive, but ultimately one of the most important. The ocean is not a passive container for redistributed meltwater. It is an active, dynamic system whose circulation patterns can exchange angular momentum with the solid Earth on timescales ranging from seasons to centuries. The primary mechanism is ocean bottom pressure. When water redistributes across ocean basins, the pressure it exerts on the ocean floor changes. Since the ocean floor is part of the solid Earth, changes in that pressure distribution change the torques acting on the planet. The equatorial ocean basins, where the Coriolis effect organizes flow patterns differently than at higher latitudes, are particularly important for angular momentum exchange. El Niño and La Niña events, the periodic warming and cooling of the tropical Pacific, produce measurable fluctuations in the length of the day. During El Niño, as warm water shifts eastward across the Pacific and wind patterns reorganize, the angular momentum exchange between the ocean and the crust produces a detectable deceleration of the surface rotation. During La Niña, the reverse happens. The interannual variability in day length that scientists have been tracking since the 1970s carries the fingerprints of these climate oscillations. What is changing in the present is that the background state against which these oscillations operate is shifting. The mean ocean circulation, the large-scale patterns of warm and cold water transport that set the context for El Niño and La Niña cycles, has been changing. The Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream and carries warm water northward and cold water southward in the Atlantic Ocean, has been weakening. Multiple independent measurement approaches, including ocean temperature profiles, current velocity measurements from moored instruments, and proxy records from sediment cores, show a weakening trend that accelerated in the mid-2010s. The Atlantic meridional overturning circulation is driven by density differences between warm, salty surface water in the tropical Atlantic and cold, dense, deep water that sinks in the North Atlantic. As Greenland melts, fresh water pours into the North Atlantic, reducing its salinity and therefore its density. Less dense water sinks less efficiently. The sinking that drives the circulation weakens. The overturning slows. A slower Atlantic meridional overturning circulation redistributes ocean heat differently. It changes the pressure field at the ocean bottom. It affects how much heat reaches the Arctic, which affects sea ice extent, which affects the albedo of the Arctic surface, which affects how much solar energy is absorbed there, which affects atmospheric circulation patterns. Each of these downstream effects carries its own signature in the rotation data. The jet stream, the high-altitude wind current that circles the globe in the mid-latitudes, is sensitive to the temperature contrast between the Arctic and the mid-latitudes. As the Arctic warms faster than the rest of the planet, that temperature contrast weakens. A weaker contrast produces a less stable jet stream, one that meanders more dramatically in large looping patterns called Rossby waves. These meandering patterns shift where storm systems form and how they track across continents. They also affect the distribution of atmospheric mass across latitudes, which directly affects the angular momentum of the atmosphere, which directly affects the angular momentum of the crust. The total angular momentum of the Earth-atmosphere system is conserved. When the atmosphere shifts its angular momentum, the solid Earth compensates. This is why meteorologists and geodesists work closely together. A severe atmospheric circulation pattern over one hemisphere can be detected as a small but real change in the length of the day. The atmosphere is not separate from the rotation story. It is one of its chapters. What is new in the current period is that multiple atmospheric, oceanic, cryospheric, and deep Earth signals are all changing simultaneously. The system has never, in the instrumental record, been in this configuration before. Extending into the pre-instrumental record using geological proxies provides some guidance, but the modern configuration of ice sheets, ocean circulation, and geodynamo state does not have a clean analog in the past few 100,000 years. The inner core reversal hypothesis, if confirmed, would add yet another layer to an already complex picture. Some theoretical models suggest that the inner core oscillates between periods of faster and slower rotation relative to the mantle on timescales of decades to centuries, driven by gravitational coupling from the mantle and electromagnetic coupling from the outer core. If this oscillation is real, the current reversal might be the beginning of a new phase rather than a one-time event. The models predict that the surface effects of such an oscillation would appear with a time lag of years to decades, consistent with what the current data shows. Other models suggest the inner core behavior is more episodic, driven by intermittent instabilities in the outer core circulation rather than by a regular oscillation. Under this view, the current episode might be a transient rather than the beginning of a long-term trend. Distinguishing between these possibilities requires more seismic data collected over longer time periods. The seismographic record sensitive enough to probe inner core rotation only reaches back to the 1960s with good global coverage, and to the 1930s and 40s in limited regional coverage. For a process potentially operating on decadal to century timescales, 60 years of data is a short window. Future seismic networks will help. There are proposals for ocean-bottom seismograph arrays that would provide better coverage of the southern hemisphere, where the inner core's crystal anisotropy, the directional dependence of seismic wave speed, is particularly informative. Better coverage would allow researchers to distinguish between rotation of the inner core and changes in the crystal structure at the inner core surface, the two competing explanations for the seismic observations. Getting that distinction right matters enormously for understanding what is driving the surface rotation anomaly. What is already established, regardless of how the inner core debate resolves, is that the outer core's behavior has changed. The magnetic field observations from SWARM and earlier missions leave little doubt that the flow patterns in the liquid outer core are different today than they were 50 years ago. The changes are not catastrophic by geological standards. They are, however, outside the range of variability captured in the modern satellite record. And they are occurring at a time when multiple other Earth systems are also departing from their historical baselines. The coincidence of timing across these different systems is the most important scientific observation of the moment. Not the individual changes, each of which is remarkable on its own terms, but the fact that they appear to be moving together. Scientists use a specific phrase for this kind of observation: force synchrony. It refers to a situation where multiple systems that are normally only loosely coupled begin to move in a correlated way because a common driver is pushing them all in the same direction simultaneously. The driver does not need to affect each system through the same mechanism. It just needs to be strong enough and broad enough to perturb multiple systems beyond their normal range of independent variation. In Earth's case, the candidate common drivers include changes in the geodynamo state that could simultaneously affect the magnetic field, the electromagnetic torque on the mantle, the surface rotation, and through the magnetosphere, even the ionosphere and atmospheric circulation. They also include the ice sheet changes, which redistribute mass affecting the rotation directly, shift the rotation axis, alter sea level patterns, introduce fresh water into the ocean affecting circulation, and change the albedo of the polar regions affecting atmospheric heat transport. And they include the possibility that both are themselves responses to something even deeper, a change in the heat flow pattern at the core mantle boundary that affected both the geodynamo and, through mantle convection, the long-term behavior of the tectonic system that controls where heat emerges at the surface. That deepest level of the story is the most speculative, but it is not without precedent. The geological record shows periods, called supercrons, when Earth's magnetic field remained stable in one polarity for tens of millions of years, and periods of rapid reversal frequency. These modes appear to correlate with the configuration of the tectonic plates and the pattern of subduction, where cold ocean crust descends back into the mantle at the margins of continents and island arcs. As cold slabs descend through the mantle and eventually arrive at the core mantle boundary, they change the thermal structure there. They create cold, dense regions that affect how the outer core convects, which affects the geodynamo, which affects the surface rotation. The timescale for this mechanism is millions of years, too slow to explain the changes we are observing in the present. But it illustrates the principle. Earth systems are connected across all scales, from the daily to the geological. The same logic that links tectonic plates to geodynamo behavior across millions of years operates, in different form and on different timescales, in the changes we are measuring today. The instruments we have built to track these changes represent one of the most impressive scientific achievements of the 20th and 21st centuries. The network of atomic clocks, the global seismograph arrays, the magnetic satellites, the gravity missions, the ocean monitoring systems, the ice-penetrating radar surveys, the geodetic VLBI networks, together they constitute a sensory system for the planet itself. We are reading Earth's vital signs in real time with a precision that was impossible even 30 years ago. And what the vital signs show is that the planet is in a period of elevated activity across multiple systems simultaneously. The baseline shifts that started becoming visible in the instrumental record around 2010 to 2015 were not predicted by the models operating at the time. The fact that they were not predicted is itself important. It tells us that the coupling between Earth systems is stronger than those models assumed, or that the systems are sensitive to thresholds and tipping points that the models had not adequately characterized. The scientific response to this situation has been to increase monitoring, improve models, and extend the observational record both forward into the future and backward into the geological past. New paleomagnetic studies are recovering field behavior records at higher time resolution than previously available. New seafloor sediment cores are providing better records of past ocean circulation. New ice cores from Greenland and Antarctica are extending the atmospheric record further back in time. New seismic networks are accumulating the data that will eventually allow the inner core question to be resolved. This is science at its most essential. The confrontation between what the observations show and what the models predict, with the gap between them driving the next generation of questions and the next generation of instruments to answer them. What is happening to Earth right now is scientifically unprecedented in the instrumental record. That does not mean it is catastrophic. Earth has done more extreme things throughout its history, but it does mean that the tools we use to navigate the modern world, the clocks, the satellites, the grids, the communication networks, are being asked to operate under conditions their designers did not plan for. And it means that the people responsible for maintaining those systems, the engineers, the policymakers, the scientists whose models guide infrastructure decisions, are working with less certainty about the future behavior of the planet than they had a generation ago. That uncertainty is not a failure of science. It is the honest acknowledgement that we are watching a complex system change in real time, faster than some of our best models predicted, and that we need better models and more data to understand where it is going. The planet is not sending us a message. It is not capable of intention, but the data it is generating is telling us something important about the limits of our assumptions and the need to build systems that are more adaptive and more resilient to a wider range of geophysical conditions than we have historically planned for. How fast the current changes proceed and where they stabilize will be among the defining scientific questions of the coming decades. The answer is being measured right now by instruments we have deployed across the surface and in orbit around a planet that has been turning, changing, and surprising us since long before we were here to watch. To understand just how radical the inner core reversal finding actually is, consider what it took to discover it in the first place. The inner core is roughly 3,600 miles below where you are standing. No drill, no probe, no instrument has ever physically reached it. The deepest borehole ever drilled, the Kola Super Deep Borehole in Russia, reached just under 8 miles before the project was abandoned in 1989. The inner core is more than 400 times deeper than that. The pressure at its surface is 3 million times atmospheric pressure. The temperature exceeds 9,000 degrees Fahrenheit. No material we have ever engineered could survive long enough in that environment to send back useful data. And yet we know the inner core exists. We know it is solid. We know it is composed primarily of iron. We know its approximate density, its crystal structure orientation, and now, apparently, something about its rotation rate. All of this knowledge comes entirely from seismic waves. When a large earthquake occurs, it sends energy radiating through the planet in all directions. Some of that energy travels as compressional waves, called P waves, which push and pull material in the direction of propagation. Some travels as shear waves, called S waves, which move material perpendicular to the propagation direction. Shear waves cannot travel through liquids. They are absorbed completely when they encounter the liquid outer core. This is one of the primary pieces of evidence that the outer core is indeed liquid. Shear waves generated by earthquakes on one side of the planet do not appear at seismographs on the other side in the geometry expected for a solid core. Compressional waves do travel through the outer core, but they are refracted significantly at the liquid-solid boundary where the outer core meets the inner core. The refracted waves that pass through the inner core are called PKIKP waves, where the letters stand for P wave, K for core, I for inner core, K again for outer core on the way out, and P for the final P wave leg through the crust. By comparing the travel times of PKIKP waves that pass through the inner core to the travel times predicted by models of a non-rotating, symmetric inner core, scientists can detect anomalies that reveal something about the inner core's actual structure. The key insight is that the inner core's iron crystal structure is not isotropic, meaning it does not transmit seismic waves at the same speed in all directions. Because the crystals are partially aligned by the magnetic forces in the outer core, seismic waves traveling roughly parallel to Earth's rotation axis pass through the inner core slightly faster than waves traveling in other directions. This anisotropy is the inner core's fingerprint. If the inner core is rotating relative to the mantle above it, that fingerprint rotates with it. The same earthquake source, sending waves through the inner core along the same path, will show a slightly different travel time in one decade compared to another because the crystal alignment has shifted slightly relative to the path the waves take. By comparing seismograms from earthquakes in the same location recorded at the same station decades apart, scientists can look for exactly this kind of systematic shift. This is what the Yang and Song study of 2023 did with exceptional care. They used repeating earthquakes, events that occur in the same location with the same mechanism, producing essentially identical seismic signals at any given station. The advantage of repeating earthquakes is that the source is controlled. Any differences in the recorded waveforms must reflect changes in the path the waves took, specifically in the properties of the inner core. Their analysis found that the pattern of travel time anomalies had reversed sign. In the 1990s and early 2000s, waves through the inner core arrived systematically faster or slower than predicted, in a way consistent with the inner core rotating faster than the mantle. By around 2009, the anomaly had nearly zeroed out, consistent with the inner core rotating at the same rate as the surface. After that, the anomaly changed sign. The pattern was now consistent with the inner core rotating slightly more slowly than the surface. The simplest interpretation? The inner core reversed its relative rotation. But seismology rarely offers only one interpretation. The critics raise legitimate points. The inner core surface is not smooth like a billiard ball. It is topographically complex, with irregularities in the density and crystal structure at its outer boundary that could scatter seismic waves and change their travel times without any rotation occurring. If those surface irregularities change over time due to crystallization of new iron at the inner core boundary or remelting of existing material, the seismic signature could evolve in a way that mimics a rotation signal. The debate cannot be resolved with the current dataset. It requires a longer time series of seismic observations and, ideally, better coverage of the inner core's properties in 3 dimensions. Future seismograph arrays, particularly those designed to fill gaps in the current global network in the southern hemisphere and the oceans, will be critical for resolving this question. But here is what makes the inner core story scientifically compelling, regardless of whether the reversal is ultimately confirmed. Even if the inner core did not reverse, something changed in its rotation behavior around 2009 to 2012. The over-rotation that was observed through the 1990s clearly slowed. That deceleration, even without a reversal, would transfer angular momentum to the outer core. The outer core would transfer it to the mantle. The mantle would transfer it to the crust. The physics of angular momentum conservation ensures that a deceleration of the inner core must be accompanied by an acceleration of something above it. The surface is the end of that chain, and the surface is faster. The question of coupling timescales, how long it takes for a change in the inner core's rotation to appear as a change in the surface rotation, is one of the most intensely studied problems in geodynamics right now. The coupling is electromagnetic. Electric currents in the outer core interact with the magnetic field to transmit torques between the inner core and the mantle. The strength of this coupling depends on the electrical conductivity of the mantle at its base, the core-mantle boundary region, and on the structure of the magnetic field there. Different studies have estimated coupling timescales ranging from a few years to a few decades. If the timescale is a few years, the inner core change in 2009 to 2012 would begin showing up at the surface by 2012 to 2015. If the timescale is longer, the surface effect would appear later. The observed onset of clear surface acceleration around 2016 is broadly consistent with a coupling timescale of a few years to about half a decade. The correspondence is close enough to be taken seriously, but not close enough to be definitive. This is the epistemic situation in deep Earth science right now. A web of correlations and physical arguments that together point strongly in a consistent direction, but without the direct measurements that would close the case. The instruments needed to close the case either do not yet exist or have not been deployed long enough to accumulate a sufficient data record. In the meantime, the surface keeps accelerating, the magnetic field keeps weakening, the ice keeps melting, the pole keeps drifting, and the research community keeps measuring. There is a broader lesson embedded in this story that goes beyond the specifics of Earth's rotation. Scientific systems, like planetary systems, are complex and coupled in ways that are not always apparent until something changes. Our civilization built its physical infrastructure, its timekeeping systems, its navigation architecture, its electrical grids, during a period of unusual geophysical stability. The stability felt permanent because it persisted across the entire span of recorded human history. But geological time is not human time. What feels permanent on a human scale can be a momentary quiet in the geological record. The atomic clock network exposed this by becoming sensitive enough to detect the planet's own variability. Before atomic clocks, Earth's rotation defined time and the discrepancy was invisible. With atomic clocks, the discrepancy became measurable. And what the measurement revealed was that the planet's rotation was never as stable as we assumed. It fluctuated constantly, it varied seasonally, annually, decadally, and now it is departing from its expected trajectory in a way that the models did not predict. There is a useful analogy in engineering. When you design a structure, you build in safety margins. You assume the loads the structure will experience over its lifetime and add a buffer to ensure it can handle more than expected. The challenge comes when the actual loads consistently push against the design margins rather than sitting comfortably within them. At that point, the question is not whether the structure will fail immediately, but whether the accumulated stress is revealing a design assumption that needs to be revisited. Our global digital infrastructure was designed around the assumption that Earth would rotate within a predictable range, that the poles would remain stationary enough that the coordinate systems built around them would stay valid, and that the magnetic field would provide reliable shielding for the satellites we deployed. Each of these assumptions is being tested in the present. None of them are failing catastrophically. But the safety margins are being consumed at a rate that was not planned for. The engineering community's response has been practical and relatively quiet. The network time protocol is being updated. The coordinate reference frames used by navigation systems are being updated more frequently than in previous decades. Satellite operators are adjusting their shielding and redundancy for the South Atlantic Passage. Power grid operators are adding monitoring for geomagnetically induced currents. These are manageable adaptations, and the people responsible for implementing them are capable and well-resourced. But the adaptations assume the changes proceed at roughly the current pace. If any of the accelerations described in this video continue to steepen, if ice loss accelerates beyond the rate the new models project, if the magnetic field weakening picks up speed, if the surface rotation anomaly grows larger, the engineering response needs to grow with it. And that scaling requires lead time that is measured in years to decades, not months. This is the practical reason why the science described here matters beyond its intrinsic fascination. It is not just a story about a planet doing something unexpected. It is a story about the gap between the physical world and the assumptions built into the systems that 7 billion people depend on every day. The scientists tracking these changes are not alarmists. They are, by training and culture, deeply skeptical of dramatic claims. The papers they write are filled with uncertainty ranges, competing hypotheses, and carefully qualified conclusions. What they are is consistently surprised. The data keeps coming in faster and larger than the previous generation of models predicted. Not every measurement, not every data point, but the trend across systems is in the direction of faster change, not slower. That consistent pattern of faster than expected change across independent systems, measured by independent teams using independent instruments, is what demands attention, not fear. Attention. Scientific attention to close the remaining gaps in our understanding. Engineering attention to harden the systems that are most vulnerable. Policy attention to ensure the resources needed for both are actually available. The planet has been managing its own geophysical transitions for 4.5 billion years without our assistance. It will continue to do so. The transitions that matter on human timescales are the ones that stress the infrastructure we have built on and around it. And the science described here is increasingly showing that we are in one of those transitions right now. What makes this moment genuinely exciting, beyond the challenges it presents, is the quality of the tools we now have to understand it. No previous generation of humans had access to satellite gravimetry, global seismograph networks, magnetic field missions, atomic timekeeping, and global positioning systems simultaneously. The convergence of these technologies in the last few decades has produced a revolution in our ability to see the planet's interior processes from the outside. We are, for the first time in human history, watching the deep Earth in something close to real time. Every seismic event is catalogued and analyzed. Every magnetic field fluctuation is recorded and interpreted. Every millimeter of ice loss is measured from orbit. Every millisecond deviation in the day length is tracked and published. The planet is being read with a fidelity that would have seemed like science fiction to the geophysicists of a century ago. And what the reading is showing us is a planet that is more dynamic, more tightly coupled, and more rapidly evolving than we previously understood. That is not a reason for despair. It is a reason for continued investment in the science that allows us to understand it and in the engineering that allows us to adapt to it. The story of Earth's rotation is ultimately a story about the limits of the assumptions we build our world on, and about the scientific process that allows us to discover and refine those limits before they become failures. The planet keeps spinning, slightly faster than it was. The data keeps coming in, the models keep improving, and our understanding of the world we live on keeps deepening, one carefully measured millisecond at a time. What happens over the next few decades in each of the systems described here will be among the most scientifically consequential observations in the history of geophysics. The instruments are in place, the researchers are watching, and the planet, as it always has, continues to surprise. One aspect of this story that rarely gets the attention it deserves is how the measurement of Earth's rotation has transformed our understanding of what a scientific measurement even is. When you say Earth rotated faster on June 29, 2022, what you are actually saying is extraordinarily complex. You are comparing a count of cesium atom oscillations to the observed angle between Earth's surface and a set of reference points in distant space. You are correcting for the proper motion of those reference points. You are accounting for the gravitational lensing of the light from those reference points. You are subtracting the effects of atmospheric refraction on the radio waves used to observe them. You are applying corrections for the elastic loading of the ground beneath the telescopes. And after all of that, you are reporting the result in a coordinate system whose origin has been carefully defined by international agreement. The length of day is not a simple reading off a meter. It is the end product of a global scientific infrastructure involving dozens of institutions, hundreds of scientists, and a framework of reference frames and physical constants built up over more than a century of collaboration. The fact that this infrastructure can detect a millisecond scale change in the rotation of a planet is one of the greatest achievements of applied physics and international scientific cooperation in human history. And it is detecting something real. The checks have been run, the calibrations have been verified, the data has been cross-referenced between independent systems. The signal is not an artifact of measurement error, it is a signal from the planet itself. Understanding the atmospheric contribution to rotation variations requires understanding something called atmospheric angular momentum. The atmosphere is not stationary. It circulates in complex global patterns driven by differential heating from the sun. Those circulation patterns carry angular momentum. When the atmosphere accelerates in the east-west direction, it does so partly at the expense of the solid Earth's rotation and partly by tapping into the Earth's angular momentum reservoir. The exchange is mediated by friction at the Earth's surface. The atmospheric angular momentum budget is dominated by the upper tropospheric winds, particularly the jet streams. When the westerly jets strengthen, they extract angular momentum from the solid Earth and slow its rotation slightly. When they weaken, they give angular momentum back and the planet speeds up slightly. The interannual variations in jet stream strength associated with the El Niño Southern Oscillation are responsible for some of the most clearly visible signals in the length of day record. What is changing in the current period is the background state of the atmosphere. As the Arctic warms at roughly 2 to 4 times the global average rate, the temperature contrast that drives the polar jet stream is weakening. A weaker temperature contrast produces a weaker, more sinuous jet. A more sinuous jet redistributes angular momentum differently. The signature in the rotation record is subtle, but it is there, and it is pointing in the same direction as the other signals, toward a planet whose rotational behavior is departing from its 20th century baseline. The tropical atmosphere also plays a role through a phenomenon called the quasi-biennial oscillation, a regular alternation of east and west winds in the stratosphere above the tropics that cycles with a period of roughly 28 months. This oscillation has been one of the most regular features of atmospheric dynamics observed in the instrumental record. Then, in 2016, it broke down. The expected transition from westerly to easterly winds was disrupted by an unusual pulse of westerly winds from the extratropics. The quasi-biennial oscillation has since recovered and is continuing, but the 2016 disruption is considered highly anomalous and was attributed partly to changes in the tropical wave forcing of the stratosphere associated with the altered circulation patterns in the lower atmosphere. The quasi-biennial oscillation affects global atmospheric circulation in ways that show up in the rotation record. Its disruption in 2016 added another layer of atmospheric forcing to a rotation signal that was already departing from its expected behavior. The coincidence of timing with the peak of the surface acceleration record in 2020 and 2022 may be partly explained by the cumulative effect of multiple atmospheric anomalies piling up over the same period. This is the fundamental challenge in attributing Earth's rotation changes to specific causes. Multiple factors are operating simultaneously. Some reinforce each other, some partially cancel. The net rotation signal is the sum of contributions from the inner core, the outer core, the mantle, the atmosphere, the ocean, and the ice sheets, each of which is itself changing, each of which interacts with the others. Untangling these contributions is a problem of numerical complexity and data quality that will occupy Earth scientists for decades. The practical work of keeping global systems synchronized in the meantime falls to a small number of institutions that most people have never heard of. The International Earth Rotation and Reference Systems Service, headquartered in Paris, is the primary organization responsible for monitoring Earth's rotation and publishing the measurements that feed into global timekeeping. It coordinates observations from the global VLBI networks, the global network of laser ranging stations that track the orbits of precisely positioned satellites, and the global network of GPS receiving stations that form the backbone of modern geodesy. It processes all of this data and publishes daily and weekly estimates of Earth's orientation in space, along with the offset between atomic time and astronomical time. These publications, the Earth orientation parameters, are not merely of academic interest. They are essential inputs for every application that depends on knowing precisely where on Earth is located in space. Navigation satellites use them, spacecraft trajectory calculations use them, Geodetic surveys use them. Deep space antenna networks use them to point precisely at distant probes. The International Earth Rotation and Reference System Service is, in a very real sense, part of the operating system of the modern world. And the organization has been publishing updated Earth orientation parameters more frequently in recent years as the rate of change of Earth's orientation has exceeded the update frequency that was standard when the system was established. The changes are manageable. The infrastructure adapts, but the rate of change is a data point. The planet is more variable than the systems designed to track it expected it to be. There is a philosophical dimension to this story that is worth acknowledging directly. Human civilization is built on the assumption of a stable physical world. The mountains will stay where they are. The sea will remain at its current level. The day will last 24 hours. The compass will point north. These assumptions are not random cultural choices. They reflect the extraordinary stability of Earth's physical environment over the 10,000 years of post-glacial civilization. That stability is not the norm on geological timescales. It is an accident of timing. We happen to have built our civilization during one of the quieter geophysical intervals in Earth's recent history. The last ice age ended, the ice sheets retreated, coastlines stabilized. The magnetic field settled into a configuration that has remained relatively stable for several 100,000 years. The rotation settled into a range that has been predictable within narrow bounds. The tectonic system, always active, has been on a relatively quiet patch without the major supercontinent assembly or breakup events that dramatically alter global circulation patterns. In this quiet period, we developed agriculture, we built cities, we developed writing and science and global communications, we sent probes to the outer solar system, we mapped the interior of the planet using instruments sensitive enough to detect the rotation of a solid sphere 3,600 miles underground. And we built our entire technological civilization on the physical assumptions of that quiet period. The data now showing that the quiet period may be ending, at least in relative terms, is not a message of doom. It is a prompt to think carefully about which assumptions are built into our infrastructure and which of those assumptions are now being challenged. The answer will determine what kind of engineering and policy responses are proportionate and timely. The scientific community is doing its part. The global monitoring systems are being expanded and upgraded. The models are being improved. The data is being collected with unprecedented precision and published with unprecedented speed. The international scientific organizations responsible for maintaining reference systems are adapting their publication schedules to match the rate of change of the planet they measure. The missing piece is the connection between the scientific knowledge and the engineering and policy decisions that should follow from it. That gap is not unique to this topic. It appears in virtually every area where long-term scientific trends intersect with short-term institutional decision-making. The challenge is to close it before the physical changes stress the systems beyond their adaptive capacity. Earth keeps turning, a little faster than it used to. The inner core keeps moving. The magnetic field keeps shifting. The ice keeps melting. The pole keeps drifting. The instruments keep measuring. The data keeps coming in. And somewhere in that continuous stream of numbers, each one a precise measurement of some aspect of the planet's physical state, is the answer to the question that motivates all of this science. What exactly changed in the early 2010s? What drove the coordinated departure of multiple Earth systems from their historical baselines? And where is the trajectory heading? The seismographs will have something to say. The magnetic satellites will contribute their observations. The gravity missions will track the ice. The atomic clocks will count the milliseconds. And slowly, through the accumulated weight of measurement and analysis, the picture will sharpen. It always does. That is what science does. It takes the planet's own signals and translates them into understanding. We live on a world that is enormously old and endlessly active. The processes that shape it operate on timescales from microseconds, the timescale of seismic wave propagation, to billions of years, the timescale of the geodynamo's existence. Human civilization occupies a narrow slice of those timescales. The science described in this story is our attempt to read the signals from the timescales above and below us, to understand the world we inhabit more fully than its surface appearance would suggest. The rotation anomaly that started this story, a day 1.59 milliseconds shorter than any previously recorded, is a small number, but it opens into an enormous landscape of scientific questions, each connected to the others, each revealing something about how the planet works, and each contributing to the most important project in Earth science right now. understanding the planet well enough to predict and adapt to what it does next. There is one more thread in this story that has not yet been fully pulled. It concerns the oceans not as passive recipients of melted ice, but as active participants in a circulation system that is itself changing in ways with direct consequences for global heat distribution, atmospheric behavior, and ultimately for the geophysical systems at the heart of everything described here. The Atlantic meridional overturning circulation deserves a longer look than it typically gets in discussions of Earth's rotation. This circulation system, which includes but is larger than the Gulf Stream, moves an enormous quantity of heat from the tropics toward the North Atlantic. It is one of the primary mechanisms by which the Northern Hemisphere's climate is moderated. Without it, the British Isles and Scandinavia would be dramatically colder. The amount of heat transported by this circulation is staggering. Estimates range from 1 to 1.3 petawatts, meaning 1 to 1.3 quadrillion watts, comparable to the total output of roughly 60,000 nuclear power plants operating continuously. When this circulation is strong, it moves warm surface water northward, where it releases heat to the atmosphere, cools, becomes denser, and sinks to the deep ocean. The sinking water then flows southward along the ocean bottom, completing the circulation. The strength of this sinking, called the North Atlantic Deep Water Formation, is sensitive to the salinity of the surface water. Salty water is denser and sinks more readily. Fresh water from melting Greenland ice dilutes the salinity and inhibits the sinking. Multiple independent methods of estimating the strength of this circulation have shown weakening over the past few decades. Proxy records from ocean sediment cores suggest that the current circulation may be weaker than it has been at any point in the last 1,000 years, possibly longer. And some models, when pushed to their limits with continued freshwater input from accelerating Greenland ice loss, show the circulation crossing a threshold and collapsing dramatically rather than continuing to weaken gradually. A dramatic weakening or collapse of the Atlantic meridional overturning circulation would cause significant regional climate shifts, particularly in northwestern Europe, which would experience considerable cooling even against the backdrop of global warming. It would affect monsoon patterns across Africa and Asia. It would alter the distribution of marine ecosystems, and it would change the pattern of ocean bottom pressure distribution that feeds into Earth's angular momentum budget. Whether such a dramatic transition is likely, and on what timescale, is one of the most actively debated questions in climate science. The most recent assessments suggest the risk of an abrupt collapse within this century is low but not negligible, and that the circulation will continue to weaken. The weakening itself, even without a dramatic collapse, has detectable effects on Earth's rotational behavior that are being tracked and studied. The oceans are also changing in their heat content in ways that affect sea level beyond the simple addition of meltwater. Warmer water expands. This thermal expansion is responsible for approximately 40% of the global sea level rise observed over the past century. As the oceans absorb heat from the warming atmosphere, they expand from within. The expansion is not uniform. Different ocean basins warm at different rates. The deep ocean warms more slowly than the surface. The distribution of thermal expansion across depths and basins affects the ocean's three-dimensional density structure, which in turn affects its circulation patterns, its bottom pressure distribution, and its contribution to Earth's moment of inertia. The combined effect of thermal expansion and meltwater addition is currently raising global mean sea level at a rate of approximately 3.6 millimeters per year, and the rate is accelerating. Since the mid-19th century, sea level has risen by approximately 20 centimeters in total. But global mean sea level is, as mentioned earlier, a statistical abstraction. The actual sea level experienced at any given coastline reflects the global mean adjusted for local factors including vertical land motion, changes in ocean circulation, gravitational effects from nearby ice loss, and changes in the configuration of the geoid, the idealized surface of equal gravitational potential that serves as sea level's theoretical reference. The geoid is not static. As ice sheets lose mass, the gravitational attraction they exerted on nearby ocean water weakens. The water that was gravitationally pulled toward the poles redistributes toward lower latitudes. This produces what are called sea level fingerprints, characteristic geographic patterns of sea level change associated with ice loss from specific sources. Greenland ice loss produces a fingerprint where sea level falls near Greenland and rises disproportionately in the southern hemisphere and tropics. Antarctic ice loss produces a fingerprint where sea level falls near Antarctica and rises disproportionately in the northern hemisphere. These fingerprints are being mapped by satellite altimeters and confirmed by tide gauge networks. They are real and they are measurable. And they have important implications for coastal planning that are only now beginning to filter into the models used by governments and insurance companies to assess long-term flood risk. The science of Earth's changing rotation is ultimately inseparable from all of these other changes. They share physical mechanisms and they share timescales. The planet is a single coupled system, and the data is showing that system changing in multiple coupled ways simultaneously. What is perhaps most striking about the current scientific moment is the sheer quantity and quality of information flowing in from the instruments we have deployed. The 20th century was the century of building instruments. We built atomic clocks, seismograph networks, gravity missions, magnetic satellites, ocean profiling floats, ice-penetrating radar systems, satellite altimeters. We built the very long baseline interferometry networks. We built global positioning systems and their international equivalents. We launched space observatories that can measure not only the stars, but the shape of the planet itself. The 21st century is turning out to be the century of reading the data, and the data is telling a story. Not a simple story, not one with a clean ending, but a coherent story of a planet in motion with multiple systems departing from their historical ranges over roughly the same decadal window, connected by physical mechanisms that science is still working to fully characterize. The story does not end here. It continues in every new seismogram analyzed for inner core rotation signals, in every magnetic field map published by the Swarm satellite mission, in every ice mass estimate from the Grace follow-on satellites, in every length of day update published by the International Earth Rotation and Reference Systems Service. The instruments are running, the data is flowing, and the picture of the planet we live on is becoming clearer and more complex at the same time. That combination, clarity and complexity arriving together, is the hallmark of mature science encountering a genuinely difficult problem. The problem is not whether Earth is changing, it is. The problem is not whether the systems are coupled, they are. The problem is the quantitative one: how much, how fast, and toward what new equilibrium. Those are the questions that will define Earth science in the coming decades, and answering them will require not just better instruments, though those are essential, but a sustained commitment to understanding the planet deeply enough to plan for what it does next. Every millisecond of the day that was shorter than expected on June 29, 2022, carries information about the deep Earth. Extracted carefully through the full apparatus of modern geophysics, it points toward a planet that is more dynamic than we planned for and more connected than we previously appreciated. That is not a problem to be feared. It is a challenge to be met with the same scientific rigor and engineering creativity that built the instruments capable of measuring it in the first place. The planet keeps spinning, slightly faster than before. The observation remains unexplained in its entirety. The investigation continues. Let's take a step back and look at what the entire body of evidence is saying, because when you lay it all out together, the picture that emerges is one that Earth scientists are still processing. Consider each of these observations in isolation first. The inner core changed its rotation behavior sometime between 2009 and 2012. That is one observation. The outer core's circulation patterns, as inferred from magnetic field satellite data, shifted during roughly the same window. That is a second observation. The magnetic field's rate of weakening accelerated in the mid-2010s. Third observation. The South Atlantic anomaly expanded and deepened in the same period. Fourth. Greenland ice loss accelerated sharply from around 2012 onward. Fifth, the Atlantic meridional overturning circulation showed measurable weakening with a steeper gradient in the mid-2010s. Sixth, Arctic sea ice extent logged its sharpest multi-year decline starting around 2012. Seventh, and Earth's surface rotation accelerated, with the trend emerging clearly from noise around 2016 and reaching record values in 2020 through 2022. Eighth, 8 independent measurements, 8 independent scientific teams, 8 independent instruments, all pointing to a coordinated departure from historical baselines in roughly the same decadal window. That kind of alignment across independent observational streams is rare in geophysics. The natural world is complex and noisy. Independent measurement systems drift apart far more often than they converge. When they converge, it is because something real drove them to. The scientific community's response to this convergence has been cautious in the right way, not dismissive, not alarmist. Cautious in the sense of careful, checking each observation against alternatives, testing each proposed mechanism against the available evidence, and building confidence slowly by accumulating agreement across different approaches. The conclusion that seems to be emerging from this process is not a single dramatic event, but a systemic shift in the coupled Earth system. Multiple layers of the planet, from the solid inner core to the ice sheets at the poles, appear to have entered a phase of elevated variability in roughly the same period. The physical connections between these layers provide the mechanisms by which a change in one could propagate into changes in others, and the timescales of those connections, ranging from years to decades, are consistent with the observed sequence in which the changes appeared in the data. This does not mean the changes were caused by a single event at a single moment. The Earth system does not work that way. It means that a set of pre-existing gradual trends, some of them centuries in the making, crossed into a region of the system's behavior where the feedbacks began to amplify rather than dampen. In dynamical systems theory, this is called passing a bifurcation point. The system was in a stable regime, perturbed from its baseline by any number of forces, but consistently returning toward equilibrium. At some point in the early 21st century, the combination of those forces pushed the system across a threshold where the return toward the old equilibrium is no longer guaranteed. The new trajectory the system is on may lead to a new equilibrium not far from the current state, or it may lead somewhere further away. The models disagree, partly because their resolution of the coupling mechanisms is not yet sufficient, and partly because the system itself is in a regime for which there is limited observational precedent in the instrumental record. The geological record provides guidance here, but imperfect guidance. The conditions of the early 21st century, an ice-free or nearly ice-free Arctic Ocean, the configuration of the tectonic plates, the present state of the geodynamo, do not have a clean analogue in the past few million years. Researchers have to work with partial analogues from deeper in Earth history, from periods when similar combinations of conditions prevailed, to estimate what behavior might be expected. The uncertainties in those analogies are large, but here is the thing about uncertainty. It is symmetric. An uncertain model can be wrong in the direction of overestimating change as easily as underestimating it. The history of Earth system science in the 21st century has unfortunately been characterized by a consistent underestimation. The ice sheets have melted faster than predicted. The ocean has warmed faster than predicted. The Arctic has lost ice faster than predicted. The Atlantic circulation has weakened faster than predicted. And the surface rotation has accelerated in ways that were not predicted at all. That consistent bias toward underestimation of the rate of change is itself a data point. It suggests the models are systematically missing something, some coupling or feedback that is operating more strongly than they assume. Identifying and correcting that missing element is one of the highest priority tasks in Earth system science today. The search for the missing element is pushing research into some of the most technically demanding frontiers of the field. At the boundary between the inner and outer core, a process called translation may be operating, the inner core moving very slowly as a whole in one direction rather than simply rotating. If translation is real, it would affect the seismic signals used to infer rotation in ways that could explain some of the anomalies without requiring a reversal. Testing for translation requires seismic data from stations specifically positioned to detect the asymmetric signal it would produce. New networks are being designed with this test in mind. At the core mantle boundary, the composition of the ultra-low velocity zones, those anomalous patches where seismic waves slow dramatically, remains poorly constrained. New high-pressure laboratory experiments are trying to determine which phases of iron, oxygen, hydrogen, and silicon compounds could produce the observed seismic properties. Getting the composition right matters because the composition determines the electrical conductivity, which determines how strongly the outer core couples electromagnetically to the mantle, which determines how fast angular momentum transfers upward. In the outer core itself, new numerical simulations of the geodynamo are beginning to reach the resolution needed to capture the small-scale turbulence that is thought to play a significant role in the dynamo's behavior. Previous simulations had to parameterize this turbulence, approximating its effects rather than resolving it directly. As computational power continues to grow, simulations are becoming capable of resolving increasingly fine-scale structures. The results are beginning to reveal that the turbulence matters more than the parameterizations assumed, which means previous estimates of the coupling timescales and the response of the dynamo to perturbations may need to be revised. All of this research is ongoing. None of it will produce a final answer this year or next year, or perhaps even this decade. Earth science operates on timescales that require patience, but the rate of progress is genuinely remarkable. The combination of better instruments, more data, and more computational power is advancing the field faster than at any previous point in its history. And that progress is what makes this moment, despite all its uncertainties, genuinely exciting from a scientific perspective. We are watching a complex planetary system change in real time, with instruments sensitive enough to see the change as it happens, and with theoretical frameworks sophisticated enough to begin understanding why. The questions being asked today are sharper and more precisely formulated than they were 10 years ago. The data being collected today is richer and more comprehensive than anything available to previous generations. And the community of scientists working on these questions is larger, more globally connected, and more computationally capable than ever before. The planet is not giving up its secrets easily, but it is giving them up, slowly, reluctantly, in the form of millisecond timing anomalies and micrometer satellite position changes and nanotesla magnetic field fluctuations. Translated through the apparatus of modern geophysics, those tiny signals are building into a coherent picture of a world that is more dynamic, more coupled, and more actively changing than we previously appreciated. We live on that world. We depend on its physical stability for the infrastructure that connects us. And we are, for the first time in human history, watching it change in real time, with eyes good enough to see. That is where this story stands. The measurements are real, the trends are clear, the mechanisms are being worked out, and the most important chapter is still being written, one careful observation at a time. Here is something that puts the entire scale of what we have been discussing into a different kind of perspective. The cesium atoms in the world's atomic clocks are performing 9,192,631,770 oscillations every second. They have been doing this continuously since the 1950s, and the count has been accumulating, stored in the careful records of the world's metrology institutes. Every oscillation is a tick, every tick is a data point. And somewhere in that enormous accumulating count of ticks is the precise, irrefutable record of a planet that started rotating faster. No single person decided this. No measurement was made with the intent of finding the acceleration. It was simply there in the data, waiting to be read. That is how the deepest discoveries work. The universe does not announce them. They emerge from the accumulated weight of careful, patient, precise measurement, often years or decades after the instruments that would find them were first switched on. The researchers who built the first atomic clocks in the 1950s did not know they were building something that would one day reveal changes in the rotation of the inner core. The seismologists who began recording earthquake waveforms in the 1960s and 70s did not know they were building an archive that would eventually show the inner core slowing down. The satellite engineers who designed GRACE in the 1990s did not know their gravity measurements would eventually become one of the primary tools for tracking polar drift driven by melting ice sheets. This is how science accumulates power, not through single dramatic revelations, but through the slow building of infrastructure, data, and understanding, each generation inheriting what the previous one built and extending it further. The scientists working on these questions today are standing on the work of generations who carefully, methodically built the instruments and the knowledge base that make the current measurements possible. And the scientists who come after them will look back on this period as the one where the picture finally started to come together, where the coupling between Earth systems became visible in the data for the first time, where the inner core revealed its secrets through 70 years of accumulated seismograms, where the magnetic field's history unlocked through careful reading of ancient basalt, where the planet's own rotation became the most sensitive instrument we have for probing its deep interior. The rotation of the Earth, measured to the millisecond, felt in the drift of atomic clocks tracked by distant radio telescopes observing billion light-year distant quasars, has turned out to be a window into the deepest parts of the planet and some of the most consequential changes of our era. That is the kind of connection that makes science, at its best, not just useful but genuinely beautiful. The day on June 29th, 2022 was 1.59 milliseconds shorter than any previously recorded. That number opened a door. What is behind the door is still being explored, and the exploration continues.